Hello everyone. Today we are going to look at voltage amplifiers and op-amps or operational amplifiers as a group of kind of voltage amplifier. So amplifiers are two-port networks. Their input or output could be either voltage or current, and the output voltage or current is proportional to the input voltage or current in these amplifiers. So there are generally four different kinds of amplifiers. They could be voltage amplifiers, in which both the input and output are voltage signals, and the gain is defined as V out over VI. Or they could be current amplifiers, in which the output and input signal are current, and or you could have transconductance amplifiers, in which the output is current, input is voltage, and the gain is defined as I out over VI. Or transresistance amplifiers, in which the gain is defined as V out over I out. In this course, our focus is on voltage amplifiers. Okay. So voltage amplifiers can be accurately modeled with three circuit symbols as shown below. So if we know input resistance, output resistance, and the open loop gain of these amplifiers, we can model them with these three parameters, and we can define, in other words, we can define these voltage amplifiers. Now, a good voltage amplifier is the one that has a large input resistance and a very small output resistance. In an ideal voltage amplifier, Ri goes to infinity, so it's open loop between the input terminals, and R out goes to 0, so it's short. Now, operational amplifiers are type of voltage amplifiers. They are in fact DC amplifiers. They have very large gain. Their gain is in the range of 10 to the power of 5 or to 10 to the power of 6. So it's a very large number. And their input impedance is very large also. So they have high input impedance in the range of a few tens to hundreds of mega ohms. And their output resistance is low, less than 100 ohm, which make them perfect amplifiers. They have they possess the properties of very good amplifiers. They have their own limitations, but in terms of their input resistance and output resistance, they match the conditions of good voltage amplifiers. Now, this triangle shape is the abstract model of amplifiers. So their op-amps are shown with this triangular shape, and they have two input terminals and one output terminal. The input terminal with a negative sign is called non-inverting input terminal. Inverting input terminal. The one with positive sign is called non-inverting input terminal. This positive one is usually called VP. The node voltage at the positive terminal is called VP or V positive. And this one is VN or V negative, V sub negative for the inverting terminal. And usually we don't show the node voltage at the positive terminal or negative terminal with this voltage source symbol, so we usually omit them, and we generally show them with VN and VP. That's it. It's implied that this VP is node voltage at the positive terminal with respect to the ground terminal or reference node, and this VN is the node voltage at the inverting terminal with respect to the reference. The same goes for V out. V out is the node voltage at the output terminal, here V out, with respect to the ground terminal or the reference terminal. In addition, these op-amps are active elements, meaning that they amplify the input signal. In order to do so, they need to be powered using external power supplies. We show them with plus Vs and negative power supply, negative Vs, V sub S. Also, sometimes usually actually Vs and negative Vs is omitted, so they are not shown in this amplifier model, but that doesn't mean in the symbol of amplifier within the circuit of amplifier circuits, but that doesn't mean that they do not exist. They are there. For the amplifier to work, it needs to be powered to an external power supply. So amplifiers, these op-amps are constructed as difference amplifiers, meaning that the output is proportional to the difference between input terminals, Vp minus Vn, and that is this Vp minus Vn is called Vd, or the difference between two input terminals of an amplifier. This is the way that they're constructed, and the output is proportional to the difference between these two input terminals. Also, the other thing is that the output voltage cannot exceed a certain voltage value, which is called V saturation. So this V saturation is close to Vs, and from the negative side to negative Vs. It can be different for the positive and negative rails of the power supply. So you can have a positive or a negative Vs value, V saturation value. So you cannot exceed the voltage level that comes from your power supply at your output. So V out is always less than or equal to V saturation. And this V saturation is close to but less than V plus and negative V plus. So let's look at the inside of these triangles. That our symbol of op-amp. So op-amps consist of several transistors and some other circuit components, but we can model all of those components using three circuit parameters, which are the components of a voltage amplifier model. So two resistance, one for R in and one for R out, and the dependent voltage source A naught Vd. So this is the linear model of op-amp. There's also an ideal model of op-amp in which the input terminals are there's an open circuit between two input terminals, and the reason is that the input resistance of op-amp is very large and output resistance is very small. So in an ideal case, we can say that because this is very high, the input resistance is very high, in ideal case it's like open. So Ri goes to infinity and R out is 0, so it's short at the output and it's open at the input terminal. And in general, because this Ri is large, the input current, the current that goes to the input. So since the input current to the positive terminal or non-inverting terminal and IP and the inverting terminal, because of the large resistance, input resistance, these currents, this IN and IP are almost equal to 0. And this is the first golden rule of, this is called the first golden rule of op-amps, in which IP is almost equal to IN and both of them are equal to 0, are almost equal to 0. For the case of ideal op-amp, IP is going to be equal to IN, and that's exactly equal to 0. So let's look at the case of let's look inside this the operation of these amplifiers and how the range of signals that they can amplify. So since the gain is high, like for example you have a naught equal to 10 to the power of 5, and for example consider the case that V saturation is like for example 15 volts when Vs and negative Vs are in the range of 16 volt, for example, so it's slightly less than that. So in order for the amplifier to operate in the linear region, Vi or Vd must be equal to V out over A naught. So if you do that, so and V out is maximum. For example, V out goes to the maximum of V saturation. It's equal to 15 volts divided to the 10 to the power of 5. That's going to give me 115 microvolts. So which is a very small value. So the maximum input voltage that you can amplify here, plus minus VI, the maximum input voltage that you can amplify is 150 microvolts. So beyond that, anything beyond that, the amplifier is going to saturate to 15 volts. So you're not going to get any signal larger than 15 volts. So this is not good because you want to have a large range of input signals, input voltages that you want to amplify. In addition, this gain factor is sensitive to environmental situations and manufacturing parameters, so it's not always equal to 10 to the power of 5. So a slight variation in the value of A0 is going to mess up the value of output. So usually op-amps are not used in this open loop configuration. By open loop, I mean there is no feedback from V out to the input terminals, either positive or negative terminals of my op-amp. So we're going to see next how we can fix this situation and build a stable voltage amplifier using op-amps.